Okay, so what we're going to do now is take a look at a simple ignition system. So the first one that we'll take a look at is the Kettering system. This is probably one of the first, or one of the first developments of an ignition system, because remember, with a petrol fuel, we need to give it a spark to make it burn, to give us that power that we need, right? So how it's done is we use a device called a coil, which for all intents and purposes is a step-up transformer. Because remember, we're starting with here a 12-volt feed, right? 12.6 volts. Now, when the engine's running, that'll step up to about 14.2. But we need to step that up to make it jump the gap at the plug, right? Now, remember what we said, right? The gap at the plug, if we take a plug out of its normal environment, its combustion chamber, and hold it out in the air, it becomes quite easy for it to jump the gap here, right? But when it's inside in the combustion chamber, we have a lot of pressure, we have a swirling mixture going around and around, so it becomes harder for it to jump that gap. So we need to bang up the voltage here now, as much as we need to make that arc across this gap here, right? And that's what it is, it's an arc rather than a spark. So if we take a look at our diagram here of the simple circuit, here's our 15 here from our ignition live, our ignition switches here, and we're going to follow this circuit through. Now remember, for the ignition system, there's two parts to it. The primary circuit part is our trigger, and what it's going to trigger to happen is that coil is going to fire. So much like a gun, if that's the barrel of the gun, this is going to be our trigger over here, where we're going to pull the trigger and make it fire. Now, we all remember this from basic electricity, where if we switch on this circuit here, and if that contact is closed, current is going to flow through this primary winding here, and it's going to build up a magnetic field around the primary winding, right? As in a straight line conductor with current going through it. So, depending on, with basic electricity, the stronger the magnetic field, we're going to require more current. So, in a coil, we don't want too much current flowing through this primary, because as we've seen in the breakout of the coil, the primary winding is quite a small winding, and yet it's the bigger of the two windings, the thicker gauge winding in there. So what we're going to get here is a low voltage, 12 or 14 volts, depending on whether we're trying to start or it's running, pushing a higher current through this winding here and out to earth. And it's going to form up a magnetic field around this winding in here. To magnify up that magnetic field, to make it intensify up, right, we put in the soft iron core here, which is going to really intensify up the magnetic field as much as possible. And when we have that flowing through the circuit and out to earth, like with circuits where we switch on or off an ordinary light bulb circuit, we're going to get a little bit of a voltage spike in a light bulb circuit. Now what we want to do with this primary winding is make it a big enough surge in there that we're going to spike up that voltage extremely briefly, but from 14 volts, say for a running engine, up to approximately 200 or 300 volts, whatever we need, right? Now, as that's happening, we suddenly switch off this circuit here. This is coil in here in the primary winding is what they call fully saturated up, and it's the strongest magnetic field that it can produce. It's magnified up by the soft iron core in here, so the magnetic field is coming all the way around here, right around inside the coil. And the sudden opening of the circuit here causes it to get a pulse of magnetic action here. That's going to step me up to my 200 or 300 volts, which is what they call self-induction into the primary winding. But because it's only a very brief thing, at the same time it bulges out the magnetic field or magnifies it out and we get this sudden jump up, the magnetic field also collapses as well. And where it's collapsing back to is into this soft iron core here. So it's already all around here, the magnetic field. And as we collapse it through, as it's collapsing, it cuts through our secondary winding here. Now you can see, there's a difference here. The primary winding is the thicker of the two windings. So it's a low voltage, higher current winding. The secondary winding will have approximately 100 more turns of wire in it. But it's a much finer wire, right? So it's not going to be able to carry a whole lot of current. Possibly less than half an amp in an awful lot of cases is going to be run through this here. but we get a very low ampage in here, but a massively higher voltage coming in here, because it's going to pulse out here with this high voltage, low current, travel through the spark plug central electrode here, and we want it to jump this gap here and get back to earth. So we have to have that high voltage to make it get there. If it was an ordinary 14 volt field and we didn't step it up here, even if I produced 200 volts here from a self-induction into the primary, it probably wouldn't be enough to make that arc across that gap up there. So we have way more turns of winding here in the secondary to multiply up what that spikes up to in there when I open the circuit. So 14 volt, we say, running voltage going through at approximately 14.2. We suddenly open the circuit by breaking the primary circuit here through the use of the contact breakers. It bulges up the magnetic field very briefly, so self-induces into the primary winding, and then at the same time it bulges up and collapses, cuts through into the secondary. So we get a mutual induction taking place into the secondary. But if that's bulged up to 200 volts, and this is 100 times more windings here, what we end up pulsing out of this as a voltage is approximately 20,000 volts. So, contact breaker is what we call the trigger here. This is our firing mechanism here, our coil, right? This is how we do it here. We see in the distributor here, we have a centre shaft in here, distributor shaft, and we say, okay, for every lobe or corner that you can see on it, there's one cylinder associated with it. So, let's say that's cylinder 1, cylinder 2, cylinder 3, cylinder 4. And every time it comes around, it hits off the heel of the point here and opens it and breaks the circuit. Therefore we get self-induction and mutual induction and spark. So we pull the trigger and fire the coil. Okay, so this is a basic system, and it's really to give you an idea of how this works. And as we step through this stuff, we will see different triggers. Right? The coils themselves are basically the same. And we can see on this one here, this is the old barrel type coil that was used with the distributor systems. So we can see, right, okay, we have a feed coming into it here from our ignition switch, which we can see over on the diagram. It goes through the primary winding and comes back out here, heading for earth, but has to go through our trigger, our contact breaker points, before it gets to earth. So the coil itself is basically what we've drawn up there. Now because anywhere where voltage is getting produced like that, it's going to build up a bit of heat inside it. So inside this coil we'll have a transformer oil to try and keep the windings cool, because we're going to try and cool down that coil. And that coil itself on this type of system is going to produce the spark for every single cylinder at every single RPM. So the amount of times it's going to produce that spark per minute or per second is going to increase as engine RPM increases. But it's a basic coil system, and it runs through for all the systems all the way through, right through to where we go to distributorless systems, and then we get into getting rid of the distributor and redesigning the coil slightly in that we make it smaller, and then forward on from that we get a smaller, again, coil for coil on plug, but still the same windings and wires inside, right? And the same principle is happening inside it, where we're getting self-induction into the primary winding and mutual induction then into the secondary winding, causing it to spark, to fire the gun. Okay, so what we'll start with doing is just basic tests on this coil. Now remember, as we're doing this, as with any component, when we're testing it, we can do it with a meter, but we have to disconnect the actual coil from the wiring to do it, because we're going to do resistance tests. And remember what we said, resistance tests are only really useful for checking components. They're not useful for checking for resistance of a piece of wire or anything like that. It's only really for checking a component. So, if we were going to measure the resistance of the primary winding from the diagram, we go from one side to the other. Remember, connecting for resistance, we connect in series. We go across here. Let's turn this on to ohms. Remember, we have to zero out our meter here now. So it's a good check of the leads to make sure the leads are working as well. So we can see the internal resistance of these leads is approximately 0.1 of an ohm. Now, that means whatever I measure in here, I take 0.1 off it, and that gives me series, and there's no polarity involved in it here. So,
just can't see it.
oh, you can't see it here, Chris.
No, the actual where you're connecting it onto the coil. Just so, yeah, so they can see it. Just move your hand slightly.
Okay.
You can say, anyway.
So, we're going from one side of the primary winding to the other. Now remember, primary winding, it's the heavier gauge wire inside the coil. It will have a current going through it, of whatever, 5, 6, 7 amps maybe. So there will be a resistance inside there for a 14 volt feed. And we'll see inside here we've 1.7 ohms minus the 0.1 ohm that I have inside the leads, which gives me a 1.6 ohm resistance in this for the primary winding. Now if you remember back to the diagram, there is a connection between our primary winding and our secondary winding called the auto transformer point, right? Because when we produce a voltage in the secondary winding here, even though it's a pulse, it's a DC pulse. So for it to be DC, it has to get back to where it came from. So if this is where it got created, it comes down our plug to our plug, jumps the gap, gets back to earth. Now it has to get back to that secondary winding for it to be a DC current. So it travels back through the earth, through the battery to our 31 over here, back up to our 30 and into our 15, into our ignition switch, back through the primary winding, and gets back to this auto ignition point where the secondary is connected to it. So it makes its way back into the secondary and it's home. That's where it started its journey from, and that's where it's going to finish its journey. So what we've done there is we've connected across the positive and negative of the coil to measure the resistance of the primary winding. We got 1.6 ohms it was. So we would compare that to whatever the engine specs are to see is that winding inside its specs. And they will nearly always, for this type of thing, give you a range. So it'll be inside the range you're looking for as opposed to an exact figure. The same test we're going to do now for the secondary, but remember, we have 100 times more turns of wire in the secondary, which means that secondary winding is going to be far, far greater in length. And if you remember back to your basic electricity, one of the factors that affects resistance on a piece of wire is its length. So we're expecting that the resistance in this will be much higher because its physical length is much greater than the primary winding. So let's go and do our check on it here again. So remember, from the diagram, it doesn't matter which point I go from. So if I take it from the positive side of the battery, and again, we have an auto ranging meter up there, so it will flip between ohms, kilo ohms, mega ohms, a whole lot. And this is where the other end of the primary winding is connected, the plug into the distributor cap. So if we see there what we're connecting at, we have 6.59 kilo ohms, which is 6,590 ohms. If I change where I'm taking my connection from, I move from the plus to the minus, so we have 6,590 ohms this side. We go to this side and see what the difference is. We have 6,590, because remember, the primary winding is only going to be approximately 1.6 of an ohm now. So its difference to the reading I get here is negligible. So again, we would check our specifications for the secondary winding here to make sure that we're inside the range, whatever it's set to. Say it's set from 5 to 7 or 5 to 7,500 ohms. We're well inside the range here, but you would have to have your specs up to check to really judge whether this coil is good or not. So that's a basic check of the coil using a meter. Now, what we want to do is we're going to connect up our oscilloscope to it and just get a reading of what the primary circuit looks like when it's in action. Right? So, again, we're back to the same probe now. Our two leads here. Now, I've changed the connection from on the positive side to a clip-on connection just because it makes it handier. And remember, this one is going to clip to earth somewhere. So, I'm going to clip onto an earth up here. And let's have a look at something for a minute. If we said we are going to connect up to the positive side of the circuit. Let's see what we get. So we switch on ignition, and we're going to connect to the positive side of the circuit here just to show us that this is earth switched. So on we go on to our positive.
Crank it just to move it off the cam lobe.
Okay. What's wrong is here, it is actually up. So again, right, remember what's going to happen here. The last time we had it set to 20 volts. So if I set this back down to 20 on it here again. 20 volts.
It stopped there, Dave. You press play.
Okay. So we can see here at the minute when I turn it on, it's about 5 volts there.
You have a ballast resistor on that.
Yeah. So yeah, sorry, I forgot to talk about that actually. On this particular coil system, it's there's a ballast resistor fitted on this, which means it's going to step down the voltage from you here. So if I go to this side of the ballast, and I'll go back to the probe for this just to see, we should have, you see it there on the screen now? We've 12 volt feed there. Now when I step out the other side of the ballast here and come onto the connection, it's dropped down straight away here. And the idea of the ballast resistor is to reduce the voltage going through the coil, therefore reduce the wear on the points as they open and close to try and elongate their service life. So we'll clip back onto our positive side, but remember what's going to happen here, and this is where you take control of the oscilloscope. We know that it's going to spike up to 200 volts, 2 or 300. So we're going to have to come back into our voltage here and step it up as high as we can here. And on this system, it's 200 volts we can step it up to. Now when we look at the meter itself here now, it looks like there's hardly any voltage in, but remember what the steps are here. There's 40 volts between each of these gravicules here, stepping up through the voltage. So we're just too big for us to see here. But we want it up that high because what we want to see is what happens when we start the engine. But remember, we're on the positive side of this coil. I'm just going to stop it here. We can see there's something going on here, right? We can see there's something going on here. But because we're on the positive side, we haven't changed over and we can't see the full effect of actually what's happening here inside the coil. Because we're on a positive feed here nearly all the time. We're seeing slight spikes up and down, but we can't really make out what's happening. Now, remember, the contact breaker points are on the earth side. So if I swap my connection over from the positive side to the earth side, because we are now earth triggered or earth controlled. And I'm going to start this again and run it and see what we can see this time. So we're down to 0 here now, and we're going to start it up here on the earth side. the primary circuit is the self-induction into the primary circuit. So let's just use our tool here and zoom in at one of these and see what's happening. Okay. Pull that box out of the way there so we can see what's happening. Okay. So we're on the earth side of the coil, and when the points are open, we're actually connected to the positive side. So we're coming in here at battery voltage, whatever it is, 14.2 or so. And when the contact breaker points open, we're going to drop off the voltage here now. We're going to get this voltage drop happening here now. So current for this duration here.
Sorry, when they're closed, isn't that right?
Sorry, when the closed. Yeah, thank you. As you can see, we do make mistakes here. So contact breaker points are
open.
Now I have to get it in my head. Contact breaker points are open at this stage, and again we're connected to the air side. Now we close them. We voltage drop here now because current is flowing through the primary circuit. This length of time here that it's on here now, so current is actually flowing through the primary circuit, and we're saturating up the primary winding. It's called the dwell time, right? So when the contact points now open again, like with any circuit, we get this voltage spike. Because of the soft iron core, the magnetic field is magnified up and then suddenly breaks, and we get this voltage spike, like the circuit has just been switched off. So we see it breaking up here. Now, if we pull down our line here and see actually how far it went, right at the tip of that point there, we can see here, I don't know if you can zoom in on this for me here, we can see that the voltage spiked up to 184.8 volts. From, let's see where we started from, our next one down here, we rested on our voltage as was flowing. 14.36 is our running voltage that the alternator is producing. So the step up between our running voltage and where it peaks here is 170 volts. What we can see on the other side is actually the voltage spikes up here, and this, what we can see here, is the actual time that the plug is firing. So it's a mirror image of, almost a mirror image of our secondary circuit. But by looking at the primary, we can judge how long the actual arc took place from where we stopped the circuit to where it suddenly spikes here and the spark is finished. Now what we see afterwards here is an oscillation here. So, like with a football, if I took a football up to the top of the roof of the building and dropped it, which is where I am here, I've taken it to the roof of the building, and I'm now going to drop it. The amount of time it takes to drop is this time here, and then it starts to bounce because it wants to oscillate out back to where. And remember, it goes back to where it started, which was our 14.36 volts, ready for our next spark to take place, and we can see it happening right next to it again now, right? Because what we've zoomed in on here is 1, 2, 3, 4, 5, 6 spark events that happened. So if that was cylinder 1, cylinder 3, cylinder 4, cylinder 2, cylinder 1, cylinder 3. So that coil is producing the spark for all of them. And our primary waveform here is going to show us what just happened. Now if we wanted to again, you can see the duration of the spark. So we can drag over our line to where we just switched off the primary. And rest it just on it there. And then we want to see how long did that spark last for. Drop it just to there. And we can see the difference between the two of them here now is 1.44 milliseconds. So the spark actually lasted for 1.44 milliseconds. And let's take a look as well and see how long our dwell time was. So we come back right to where the circuit got switched on. Drop it on the line there. And we drag our line back right to where we get the voltage peak, where the circuit switches off for. And we see on here, our dwell time was 10.39 milliseconds. So the amount of time that the current was flowing through the primary winding here, building it up, saturating up the magnetic field, was 10.39 milliseconds. We got a spark then for 1 point something milliseconds that lasted, and then we oscillate out. And the oscillations are important that we see them happening because they are an indication that the coil is in good condition. If you can see anywhere between 3 and 5 oscillations, it's suggesting to us that that coil is in good condition. If we see one oscillation and it's suddenly back to 14 volts, it's an indication that that coil is maybe on the way out. So we should see a good oscillation display as well. So, very basic, what we've looked at there is our primary circuit. We see on the waveform, it's coming through here at 14.3 volts, flowing through the primary here. We get out to the contact breaker points, and when they're closed, it's flowing, which is our dwell time. When we open the contact breaker points, we self-induce a high voltage of approximately 200 volts or so into our primary winding. A sudden pulse, which mutually induces into our secondary, which gives us our spark here at our plug. So the contact breaker point is our trigger, and where we were probed was here on the coil, which meant that when the contact breaker points are open, we're connected to battery voltage here at 14 volts all the way through, and we read 14 here because the circuit is open here now. We're still on the power side because we're not connected to earth. Once that contact breaker closes, we're on the earth side of our consumer here, and we suddenly drop. So the drop is where we see the circuit closing, current flowing, which means we're building up or saturating up the magnetic field. Sorry, my camera is falling over there. Don't know whether he was at the tipple or not, but anyhow. Self-induction into the primary winding and a mutual induction into our secondary, and we get a large spark from it, right down here at our spark point tip. So, we're going to take a look at, over the next course of videos, different sparks taking place on more modern things. Now remember, when we move into electronics here, the only thing that's really changing here, because our coil remains the same, our secondary winding and our distributor cap, rotor arm, plug, the whole lot remain the same. So the only thing that's really changing is how we trigger this, how we're going to trigger this. And the reason why we moved on to this was the contact breakers needed constant maintenance, so once, twice a year to make sure the gap was all right in it and the dwell was all right in it. But they would wear away or they would slip and the gap would become larger, which would affect our dwell period here. So they needed a way of making the system less maintenance on it, more reliable. So what they actually did was change this into a type of sensor inside here, which is going to send a signal to a engine ignition control module here, which had control of the earth for the coil. So what we've done is left the coil alone and changed how we're triggering it. The same with the Hall system, again just a digital signal instead of an AC waveform, but we'll have a look at those as we go. Okay, so hopefully you can get an idea of what's happening inside the system here, and we get an idea of testing the actual coil itself here as a standalone unit with a meter, and then seeing exactly what's happening on a waveform here. Now remember, this is happening really, really fast. So the only way of capturing this is to make sure your time division is really, really low. So this is looking at 10 milliseconds per division on this here. And then setting our voltage up to the highest, because we know this is going to induce a high voltage into the primary. Okay, hopefully that's been useful, and we'll take a look at some other ignition systems in our next videos. Thank you.